All right, well, I trust you did well on quiz 26. Next section in your notes, and this is really just kind of a brief introduction. I want to talk about graphing on what's called the complex plane. Graphing on the complex plane. You'll recall as we worked with functions in Algebra 2, as we've graphed things in the past, we said you can't graph imaginary values. Not on the Cartesian plane, at least. In order to graph imaginary values or complex values, we have to use what's called the complex plane. Now the good news is it looks very similar to the Cartesian plane. But instead of axes x and y, we have what's called a real axis and an imaginary axis. Now if you happen to have graph paper, go ahead and set up a complex plane on your graph paper. If not, just kind of do as I'm doing and maybe use some little tick marks that you make yourself. But on the real axis, very straightforward. You got numbers like 3 and 6 and -3 and -6 and so forth. On the imaginary axis, you don't have numbers like that. You could probably guess what kind of numbers you have. I, 2i, 3i, 4i, 5i, 6i, 7i, 8i, right? And going down -i, -2i, -3i, -4, -5, -6i, and so forth. So your real and your imaginary values are on those two axes. This is, by the way, why I was so insistent on x and y labels. Because just because you have two crisscrossing axes, it doesn't make it the Cartesian plane. X and y labels make it Cartesian plane. Real and imaginary labels make it the complex plane. But if I wanted to graph, for instance, a 3 positive 2i on the complex plane, well, again, we don't have an x and a y, we have a real and imaginary. So I go to the 3, and I go to the 2i, and that is how we graph 3 plus 2i. If I wanted to graph -4 positive 6i, well, that's going to go -4 positive 6i. If I were to graph 1 -4i, well, that's going to fall in the 4th quadrant, over 1 and down 4i. If I wanted to graph -2 -7i, obviously that's going to go backward 2, downward 7i, here in the 3rd quadrant. Pretty self-explanatory? Not blowing anyone's brain here. All right, page 183, I want you to do 1 through 4. If you wanted to use maybe a pen instead of a pencil, or a different color of ink, or something like that to maybe use the same quick grid that you just set up. That way you don't have to set up 2 of them because, you know, mathematicians are... By the way, I'm a mathematician again, not a mathematician. Mathematicians wear capes and math hats. Mathematicians just wear nerdy math shirts, math ties, and math socks that say, I'm always right. I'm back to a mathematician again. Believe it or not, that hat is warmer than you'd think it would be. Maybe not for like people with lots of hair, but when you don't have much hair anyway keeping your head warm, you notice a considerable difference when you wear any hat at all, even a nerdy mathematician hat. And the blanket was way just really warm, exceeding warm. I've already got, 3 shirts on right now. I didn't need the blanket too. But, So sorry for my YouTube fans who disappointed to see me out of mathematician garb. Victoria, if you're watching, I'll take an autographed picture and send it to you. Jamie with the purple pen of power, and Quentin with the same black pen. All right, so I'll switch and I'll go green here, as there's a big push in society to go green. 1 plus 3i, should have been right there. -2, -3i, right there in the 3rd quadrant. 4, -3i, here in the 4th quadrant. And then -5, positive I, of course, would have been here in the 2nd quadrant. Did we get all 4 points plotted correctly?
I've not done one wrong accidentally, but I see where I should have done.
Okay, which point was it?
Let's see, I think the third one.
4, -3i. You did not have it here in the fourth quadrant?
I did not. Okay, yeah, I didn't realize it was a -3i.
Okay, so you had it up here for +3i. Okay, careful. Questions? All right. Now, really, all of that, we're not going to, I could teach a 7th grader to do that, right? So, we're not going to linger there long, but what it does do is it kind of lays the groundwork for us to then transition from this standard form, a plus bi, into another more powerful form of complex numbers. Because you see, there are two ways to describe the location of a point. One way to describe the location of a point would be to give, if you will, an x and a y, a real and an imaginary. Another way to describe a point would be to say, how far is this point from the origin? And what angle of rotation does it have? In fact, if you'll flip in your textbooks, we may or may not have time to get here later this school year. Usually I have time to at least do a little bit of an intro toward the end of the third quarter. But if you look at page 275 in your textbooks, you'll see there's an introduction to what are called polar coordinates. Polar graphing is all about distance from the origin, they call it the pole, and an angle of rotation. In fact, it even uses funny graph paper, what's called polar graph paper. And you can see here where there is a primary axis or a polar axis that measures off distances, and then it's just angles of rotation. That's another way to plot distance here. And you see, by the way they list the coordinates, it's not x, y coordinates. If you look at the example at the very top, they list the points with distance from center, or a radius vector is what it's called, and an amount of rotation from the polar axis. So sometimes this is called polar form graphing because it comes after that. We'll also call it the trigonometric form. But basically, what's the distance here? We'll call that r. And what's the angle of rotation? We'll call that theta. So a plus bi is standard form. It uses real and imaginary distances, just like XY graphing does. It just doesn't have it separated by a comma. The polar form, or the trigonometric form, however, accounts for a distance and an angle. Now, true polar form is the radius vector and the angle. For us, though, we've got to take a binomial and expand it to the same idea. Well, if you think of this value here as a, this value here as b, how would I find the r? I would find it using the Pythagorean Theorem, so that r would equal the square root of a squared plus b squared, right? How would I find the theta given a and b? Given adjacent and opposite, for instance.
Tangent?
I take the tangent, or rather the arctangent, right? The theta itself could be found by taking the arctangent of opposite over adjacent, or b over a, correct? But I can't just say r comma theta like you saw at the top of page 275, because that wouldn't equal a plus bi. How would I make the conversion then? Well, consider this for a moment. The a and the r are related by the cosine. In fact, we would say that the cosine of theta is equal to a over r. Similarly, we could say that the sine of theta is equal to b over r, correct? Given that, the a itself must be equal to the r times the cosine of theta, and the b must be equal to r times the sine of theta. So if I were to say a plus bi, that would be r times the cosine of theta plus I times r sine of theta. A plus bi. Make sense? But the r itself could be factored out as a common factor. So that gives us this form, r times the cosine of theta plus I times the sine of theta. Get that in your notes if you would. This is called the trig form. Well, trigonometric, but I'm lazy because I'm a mathematician again. The trig form of a complex number. The trigonometric form of a complex number. R times the cosine of theta plus I times the sine of theta, where r is the square root of a squared plus b squared, and theta is the arctangent of b over a. And all of that is kind of comes from the idea of how the graphing works for polar graphing. So for it, now one word of caution here. If we had, for instance, a, let's backtrack here. Let's suppose I were giving you a complex number, 3 plus 2y, and I said, I want to figure out what that would be in the trigonometric form. Well, first I have to find out what's theta, or what's r, then I have to figure out what's theta. Well, r, of course, is simply the square root of a squared plus b squared. A here, a squared would be
3.
Well, squared would be 9, and then b squared would be 4. So r must be square root of 13, right? So here's my standard form. That's going to equal the square root of 13 times the cosine of, now what's theta? Well, remember, theta is going to be the arctangent of b over a. That would be 2 over 3. On your calculator, go and take the arctangent of 2 over 3. Make sure you're in degree mode. And what do we get?
33.69.
33.69, blah, blah, blah. All right. What we'll do is we'll usually do one decimal place, and we'll say that's approximately 33.7 degrees plus I times the sine of 33.7 degrees. Now, obviously, this is a much more obnoxious way to write the number. This is so much easier to see, but you're limited in what you can do with it. This is a more powerful form, as we're going to get to in the days ahead. So this is the standard form. That's the exact same value, but written in the trigonometric form. Now, that worked out great because this is in the first quadrant of the complex plane. But what if we have this number, -4, positive 6i? Well, here's the way I'm going to recommend you do it. Always find the r the same way, square root of a squared plus b squared. Do we need to worry about negatives? You're squaring. So 4 squared, 6 squared. Take the square root, you get the square, take add them together, you get the square root of 52, though that can actually factor into 4 times 13. 2 times the square root of 13 is the r. Now, here's where I want you to not use it, kind of like here, I said, don't worry about negatives. Same thing's going to be true on the theta. We're going to take the arctangent of b over a, but remember, if you plug in a negative, it's going to assume third quadrant. Or excuse me, you plug in a negative, it's going to assume first quadrant negative angle, because arctangent's limited from -90 to 90, right? If you have a positive, it's going to assume first quadrant. Well, this isn't either of those. What quadrant is this in?
No.
Second quadrant. Back 4, up 6i, right? So what I'm going to say is don't worry about positives, negatives here. Get a reference angle, taking the arctangent of 6 over 4.
56.30.
But recognize it must be in the second quadrant. So if this is my reference angle, I'm going to take 180 minus that number on the calculator. 123.69, so we'll say 123.7 degrees. Does that make sense? The negatives are going to throw you up, so forget the negatives, both when you're squaring and when you're plugging it in, but you do have to account for the quadrant. So this number, in standard form, -4 plus 6i, becomes, in trig form, 2 square root of 13 times the cosine of 123.7 degrees plus I times the sine of 123.7 degrees. Make sense? Do this next one with me on your paper. The negative square root of 5 minus 2i. Negative square root of 5 minus 2i. First thing I want to do is find r. And r equals the square root of a squared plus b squared. What do you get if you square the a? 5. Because when you square root, you get the radicand. What do I get if I square b? 4. 5 plus 4? Square root of 9? This time r came out evenly. I like that. I like it when it comes out evenly. Then I need to find theta. Theta is found by taking the arctangent of b over a. That's going to be 2 over the square root of 5. Now again, technically the negatives would cancel anyway, but don't worry about the negative. Don't worry about positives, negatives, all of that. You're technically going to get a reference angle here. Take 2 divided by square root of 5, take the arctangent. What do we get?
41.81.
Got 32.3.
All right, there's conflict. I will settle all arguments because, like my socks say, I am always right. And I got 41.81. So 2 divided by square root of 5, and then equals, and then take the arctangent.
Okay.
Right, you might have accidentally taken 2 divided by square root of 5, and while the square root of 5 was on the screen, took the arctangent instead of an equals and then arctangent. Very probable. 41.81, blah, blah, blah. That is a reference angle, though. What quadrant are we in? Backward, downward. Quadrant 3, right? Negative square root of 5 on the real axis, down 2y on the imaginary has to put us in quadrant 3. So in quadrant 3, we're going to take 180 and add this reference angle to it. So how big is the real angle?
221.81.
221.8 when we round to just that one decimal place. So this number in the trig form becomes 3 times the cosine of 221.8 plus I times the sine of 221.8 degrees. And there's my answer. Questions on this? All right, I'm going to have you try some of these for homework this evening. I want you to do numbers 6, 8, 10, and 12 on page 183. Page 183, numbers 6, 8, 10, and 12. Practice converting these numbers into the trigonometric form. Tomorrow we'll look at taking the trig form, converting it back to standard form, so we can work with whatever we want to. We'll have a lot of flexibility, and then we should also have time tomorrow to look at the advantages. Because on the surface, again, you're like, we took something so easy and made it so annoying, right? But you're going to see some advantages to the trig form, and we'll look at those in our next lesson. Have a wonderful rest of your day, and you are dismissed.